So this is the video for security exercise 22. So security exercise 22, if you remember from lecture, we know that a baseband signal is not compatible with free space communication. So we need to upshift that frequency using modulation. And digital modulation is different than analog modulation in that the analog carrier signal is modulated by voltage pulses representing our ones and zeros. So the goal of this set of videos is to familiarize you with amplitude shift keying and frequency shift keying, which were both covered in lecture. So the actual security exercise opens with looking at a frequency shift keyed signal, which we have here. So we can see here that we have some zeros and some ones. And in the zeros, we have our our space frequency, which is our lower frequency. And then we have our mark frequency, which is our higher frequency. And what it asks us to do in the very first portion is measure the mark and space frequencies in the time domain. So using this display, you can see that I have marked out using the cursor here and here one cycle, so one period. And what we have here is the period being captured between those two cursors. So we end up with a period that I'm going to put a box around. And using this, they also give you what is the frequency. So that's going to give you the information for the frequency of the space. So this is F sub space. Okay. And on the next slide, we will have our mark frequency. So similar thing here. We have our information for F mark. Again, we have from one peak to the next peak, so we just have one cycle there, so that is our period. Okay, now this moves over into the frequency domain. So we see in the frequency domain, much like we spoke about in the lectures, or may have been spoken about in your lectures, we have what looks like two different transmissions here with these two large masses inside the frequency domain. Okay, so with that, we actually get to look at where the peaks are. So we see cursor 1, which is over here. That is this. So I'm going to go ahead and put a box around that in green. And that's where that cursor is at. So I'll go ahead and draw that line in green so that you can know that's what that cursor, that's that frequency that's annotated there. And go ahead and use magenta around cursor 2, and I'll mark that out as well. Okay. So with that, you have the frequency domain representation and the information that is carried there. Okay. Then let's look at the bandwidth. So calculating the bandwidth, we look at that null. Let's put this in purple. We look at that null left of what we have here, which is F space. And then we have the null right of what's here, which is F mark, our higher frequency. And the difference between those gives us our bandwidth for this signal. And you can see right here that information is calculated. So that equals our measured bandwidth. Okay. So one of the things that I was not able to get in the lab before they closed it all down on us was the consequences of increasing the bit rate. So this is calculated for 4,800 bits per second. So if we increased our bit rate to 9,600 bits per second, you're going to be asked in the questions, what would be the expected effect to our bandwidth, given we have a frequency shift keying modulation scheme. Okay, so this is the video for frequency shift keying. I'm going to stop this and I'll do an amplitude shift keying video here next. Alright, so welcome back, and this video is going to talk about amplitude shift keying. So the first thing that we read when we're looking through the lab is that we're going to look at a time domain, and we're going to look at our baseband signal, which is represented here, and that it's actually being used to modulate this carrier. And if you see throughout this carrier, it has the same frequency regardless of the amplitude that it has, which is a key with amplitude shift keying. We maintain our frequency. Okay, so it also gives us some more information. So for example, our high pulses are zeros and our low pulses are ones. That means in this waveform, this is a 1 and this is a 0. So one of the things they're asking us to do is measure what the voltage for a 1 pulse is. Sorry, pulse for a 1 bit. So this is going to be V sub C for a 1 bit. So the next one we're going to talk about is the voltage for a 0 bit, and we have that marked out here, annotated there. So this is V sub C for a 0 bit. Okay? And then we're actually going to use our vertical markers to go ahead and mark out what our period is going to be. And we do that. You can see that we have marked from cycle to cycle. We zoomed in a little bit from the 100 microseconds over here to 50 microseconds. And from there, we get our delta T, and then it automatically calculates our carrier frequency for us. So this is going to be F sub C, and that right there would be T sub C, period, for our carrier frequency. Okay, so now we're going to look at this in the frequency domain. What we see here is the frequency of our baseband signal, and we have one cursor all the way over at our far end of 0, and then we have another cursor right here in this location. So that goes to that first null, and that gives us, starting from 0 hertz, the delta hertz. That's the distance from 0 hertz to our first null, and this is going to be the bandwidth of our baseband signal. Okay, so next is that amplitude shift key signal and its representation in the frequency domain. And we see that we have cursor 1 right here showing us this frequency right there. And that's the frequency that we see that should correlate to our F sub C. Okay? Which we come back, see that F sub C 38.46, and here we have 40.5 kilohertz. Those are fairly close. There may be some measurement errors involved there. Okay, then let's look at the bandwidth. And here we have a image where we show that we have a cursor at the first null to the left and a cursor at the first null to the right of the peak of that signal in the frequency domain. And what we have calculated over here on the side, seeing as we have those cursors, we have the difference in that frequency. So basically what we've done is just taken the higher frequency, located at cursor 2, so this would be conceivably F max, and here we would have F min for the frequency. So to find that bandwidth, we would say that bandwidth equals F max minus F min of the signal, and that leads us to that value right there, that delta hertz, the difference between those two cursors. So that should give you the measured bandwidth using the oscope. And there's going to be some other questions, theoretically speaking, about what would happen if we increase the bit rate and how that would affect the signal. This should be enough information for you to address those questions along with the information from the text and your notes from lecture. Okay.